Today, on June 20th, 2007, we're having a conversation with Ed Feigenbaum, who's the Kumagai Professor Emeritus at Stanford University. Ed is going to be talking about his life in artificial intelligence. Before he starts, let me say that Ed has had a great career in artificial intelligence. He's known as the father of expert systems. He also is a Turing Award winner and a member of the National Academy of Engineering. Let's start, Ed, by the subject of how you originally got interested in science. What are some of the early influences in your life, your education, high school, and so on?
When I was a youngster, going back to the time when I was a youngster, and that means maybe starting at 8 or 9 or 10 years old, I'm not exactly sure which, there were a number of small influences in my life. I don't want to go into great detail about it, but my stepfather, Fred Rockman, would take me once a month to the Hayden Planetarium in New York City, which is part of the American Museum of Natural History. We lived across the river from New York City in the New Jersey side of the Palisades. And once a month at that time, because it was different than the costs of running a museum were not as expensive, the Hayden Planetarium would change its show once a month. And so once a month, my stepfather and I would go over there to see the new show at the Hayden Planetarium. And since we were there, we would go through one room of the Natural History Museum every time we went there. So I got really interested in science, but mostly through the astronomy end, which I guess it happens to a lot of young kids. It also happened that my stepfather was an accountant by trade, and he would bring home a lot of work. And he would do it at home on one of these mechanical calculators, which for people who visit the Computer History Museum, you can see examples of that. Some of them are electric driven. Actually, the one I started playing with when he had it was not even electric driven, it was mechanical driven, cranking of the wheels. And I learned to really know how to use that machine, and I was very proud of it. I would show it to my friends, and therefore I kind of had a bias toward being interested in calculating machines, which later turned out to be an interest in computing eventually. But I was a science kid. I just would read Scientific American whenever I could get a hold. I mean, every month I could get a hold of it, go to the library and get a hold of it, and I would read everything I could. And I remember, as so many other people of my generation have said, and the previous generation, one book that really sucked me into science was Microbe Hunters. We need a lot more books like Microbe Hunters that will bring a lot more young people into science now.
So these interests in science continued through high school?
Right through high school. They were my best subjects. Well, my best subjects were everything. But that is, I got A's in everything. But the ones I really enjoyed the most were math and physics and chemistry, not so much biology. I don't know whether that's a function of myself or whether the teacher was not so good, but I would get a big thrill when the math teacher would give us a problem, and I'd go home and I remember I'd work on it late into the night, and my parents would want me to go to sleep, and I just hadn't cracked that theorem yet, and when I did, I was so happy.
So toward the end of high school, when you began thinking about college, how did you decide where you might want to go, what sorts of things you might want to study?
Nils, that's a great question. And so here I am in New Jersey, on the Palisades overlooking New York City, a high school which was an academic-oriented high school. And they have and I was a straight A student, and they have an academic advisor, a woman who sort of gives you the clue as to what you should do, and the initials MIT never came up. Not once in any conversation. You would think that a kid like me would normally gravitate toward MIT and apply for a scholarship or something like that. Wasn't even mentioned. I happened to see an advertisement for the what were called at the time the Westinghouse scholarships, being offered by an engineering school in Pittsburgh called Carnegie Institute of Technology. And so, since I really needed money to go to school, I applied for one of those scholarships, and it turns out that I got a Carnegie Tech scholarship, not a Westinghouse scholarship, to go to Carnegie Tech, a four-year scholarship, so that's what I did. But nobody mentioned Harvard, no one mentioned MIT, no one mentioned Columbia, no one mentioned anything. The only other alternative that I thought of seriously was Stevens Tech in Hoboken, because then I could live at home and go to school.
So you went to Carnegie Institute of Technology in Pittsburgh. What year was that, and when did you decide that what did you decide that you wanted to study?
The year was 1952, September of 1952, and the choice of subject matter was electrical engineering. Now, question is, why was it electrical engineering why did I decide to do that as opposed to going into the physics? Well, first of all, around my family, no one ever heard of a thing called a physicist. That just was the word never came up. Secondly, my parents knew that engineers could go out and get jobs and make money. So what did I like best? Well, I really didn't like puttering around with mechanical things, so I wasn't a mechanical engineer. I wasn't really too interested in chemistry, so I wasn't a chemical engineer. Well, electrical things, that was a lot of fun. That I could do, sort of clean hands on the table. Turns out that isn't quite accurate when you get to college, but I decided to be an electrical engineer.
So as I remember from my days as an electrical engineer, you take a lot of courses in circuit theory, you have labs in which you test things with oscilloscopes. All of those things happened at Carnegie Tech, and
Yeah.
you enjoyed those sorts of courses?
Yeah, I really did, but there's a calibration we need. And that is that at Carnegie Tech, yes, we did circuits. Yes, we did what you might call abstract electrical engineering, mathematical electrical engineering. But when you got into labs, it was almost entirely power electrical engineering. These were still the days when generating power was a big deal, transmitting power was a big deal, and that's where I said the hands dirty thing breaks down, because you had to go into labs and you had to stick giant prongs into big boards, and those prongs were handling tremendous amounts of amperage and voltage, and it was really scary, and I didn't really want to do that. I sort of got my friends to go stick things in these big boards.
Lots of rotating machinery. And
yeah, lots of rotating
power
machinery.
transformers.
And they didn't have electronics until one course given in 2 semesters of the senior year, with a relatively old textbook, and it was vacuum tube electronics. Transistors hadn't really come in much into they had been invented, but they hadn't come much into the teaching of the discipline. So it was pretty much power engineering.
So there were probably some mathematics courses, differential equations,
Yeah.
courses like that too, as part of the EE curriculum.
The standard ones, yeah.
Now I know that eventually you ran into Herb Simon while you were an undergraduate. How did that all happen?
I cruised through my freshman year. Interesting stuff, got all A's, but there was something missing. You're supposed to be going to university for something other than the craftsmanship of calculus or of engineering. So I felt something lacking. So I asked my advisor if I could do something else. Can I just pick a course and do something else? Like Carnegie Tech happened to have one of the world's best drama schools in the art school. They had a whole college of arts. Or they had a design school. They had a very good English department. And anyway, there were other things to take. And I looked through the catalog, and I found a really interesting listing called Ideas and Social Change. Wow. Except it was being taught at a place I never heard of, which was on the other side of campus, called the Graduate School of Industrial Administration. And I was a sophomore. I was going to be a sophomore. It was being taught by a new instructor, Nils, you know him now, from Stanford. He's now at Stanford, James March. I decided to go over there and take that, and my advisor said, sure, go ahead and see. And March let me into the course, even though I was an undergraduate. First thing he did was to expose us to von Neumann and Morgenstern theory of games. Wow, this is mind-blowing. Couldn't believe this. And then we had a series of things like that in Ideas and Social Change, including modeling of behavior. I got really interested in that, and March was the one who, first of all, employed me in the summer of my sophomore year to do experiments in social psychology. And in fact, my first published paper was a paper with March in social psychology on the decision-making of small groups. And secondly, he introduced me to a more senior and famous professor who was working with him on a book, which, of course, as you know, was March and Simon Organizations, Herbert Simon. That's how I got to know Simon. Simon took an interest in me, helped me get a summer student fellowship in the summer of my junior year, and that led to my taking a course from Simon in the first semester of my senior year, which was called Mathematical Models in the Social Sciences. Herb Simon had done many things in his career, and after that, of course, he did spectacular things in his career. But he had accumulated a bunch of modeling exercises in social science, which he published around 1956, called Models of Man. That included differential equations models of social behavior, economic models, decision-making models, including two very famous papers that influenced the early days of AI. One of them was a behavioral theory of rational choice, which introduced the ideas of search and heuristics. And then the second one was rational choice and the structure of the environment, which introduced, it basically was the prelude to Simon's famous analogy, a metaphor of the ant on the beach. The environment shapes a great deal of behavior. Those two papers were in that book. And so and stochastic models were the last third of the course and part of Simon's book. So Simon was teaching these modeling methods and modeling motivations, techniques and so on to this small group of students. I've been trying to remember who exactly was in that group, and I have a feeling that my later colleague Julian Feldman was in that group, and also perhaps Fred Tong was in that group, but it was about 6 graduate students, not me, I'm sorry, 5 graduate students and myself making 6, I was a senior, making 6 students in the class. And that was the particular class that I tell the famous story about, where Herb Simon comes in and right after New Year's, it's a semester kind of course, so it continues on after Christmas, New Year's for a while. And he comes in and says, over Christmas, Alan Newell and I invented a thinking machine.
This was in January of 56.
And it turns out Herb dates the particular date as the peak of his career was December 15th, 1955. In his autobiography, he says that's where he hit the top of the hill. He and Newell had formulated the logic theorist on December 15th, 1955, and then they did a quick bunch of hand simulations and a little bit of non-machine programming, paper-level programming, and by the time we got back after the New Year's holiday, he mentioned that he and Newell had invented a thinking machine, and that just, what could he possibly mean by that? first of all, what does he mean by a machine? And then what can he mean by that machine doing thinking?
So was it about that time that you had your first experiences with computers? How did your contact and introduction to computers happen?
The pair of events. I was, as an undergraduate, I had been what you might call a science journalist for an undergraduate publication called the Carnegie Technical. And by the time I was a senior, I was editor of the Carnegie Technical. Or maybe when I was a junior, I was editor of the Carnegie Technical. In any case, in the course of putting together some issues of this undergraduate publication, one of the issues concerned a new thing called a computer, what that might be like. But that didn't have much impression on me. What the impression was, where the impression came in was when we asked Herb in that class, what do you mean by a machine? And he handed us an IBM 701 manual, early IBM vacuum tube computer. It was their first commercial binary computer product. They, of course, had a lot of, scientific computer product. They had a lot of commercial computer products in the punch card area, punch card calculators. But at one point they introduced a binary machine for scientific calculation and a character-oriented machine for commercial calculation, the 701, 702. They were both vacuum tube computers. Herb gave us a manual, and that was a born-again experience. That was taking that manual home, reading it all night long. By the dawn, I was a born-again, or I shouldn't say born-again, just I was just hooked on computers and decided that what I had to do was, first of all, got to learn more about these things. Carnegie Tech did not have any computers at that time. So I got a job at IBM for the summer of 1956 and in New York. Had to earn some money for graduate school, but where was I going to do graduate school? Well, I was going to do graduate school with Herb Simon. Oh, and his colleague, Alan Newell, who, I'll tell you a little bit about that, but I was going to stay with Simon and get my PhD at Carnegie in the Graduate School of Industrial Administration.
So was getting a PhD on the horizon for quite a long time while you were an undergraduate, or was this a sudden decision as a senior?
Completely sudden decision, a tremendous shock to my parents. They had never heard of this idea, and anyway, engineers could get a job and earn money, and why were you going after a PhD when all that was just a fellowship that keeps you in school? And that was a kind of bizarre idea for my family. But so it just sprung up at the time when I got involved with Herb in this AI work, or maybe a little bit before, when I got involved with March and Simon on various social science things, and the idea that if you wanted to continue to do that, you better get a PhD. But it certainly wasn't a long-term plan. And during the spring of my winter and spring of my senior year, I was actually doing interviews. I actually came out here to Palo Alto to do an interview at a place called, I believe it was Raytheon at the time, had a Palo Alto location. But that was just to be an engineer.
So then in the summer, between your undergraduate and graduate work, you were at IBM having a summer job.
Yeah,
what did you do there?
I went to New York. I could live at home then. IBM sent me to the Watson Laboratory at Columbia, where they had a 650. And at Watson Lab, I learned how to program the 650. Because by that time it became known that Carnegie Tech was going to get a 650 in the summer. So I better learn the 650 so I can go back and be a user of it. Secondly, they taught me, believe it or not, wired board programming. And I'll bet almost no one hearing this question and answer session knows what a wired board program thing is, but it had 16 registers and a lot of wires that transferred signals from one register to another, and you had 16 instructions, and you could manipulate cards. So they taught me that, and then they took me back to downtown near 590 Madison Avenue around the corner in a brownstone where the graduate students were for the summer, and taught me the IBM 704, which was the successor machine to the 701, which was good because its architecture was virtually identical to the 701. I think maybe there was an introduction of index registers to the 704 that the 701 didn't have, but other than that, it was easy for me to program that. And then I did work for them in the summer.
Then, how did you get interested in programming other than these wired boards and so on? And what sorts of what was your first programming language, and when did you start getting more involved with the sorts of programming languages used in AI?
There were two things going on that essentially going on in parallel that that constituted my first important programming experiences other than the summer job at IBM. When I got back to Carnegie Tech in September of 1956 and began my graduate work, there was a 650 there, and there was a lot more than that. There was Alan Perlis, a wonderful computer genius. Later, I think the first Turing Award winner was Alan Perlis, and two other people who were assisting Al Perlis in setting up this IBM 650 for Carnegie Tech. Joe Smith and Hal Van Zorn. And later, they were joined by Art Evans, who a lot of us know as one of the big contributor to early computer science at Carnegie Tech. Perlis was finishing up an amazing thing called a compiler, which was IT, internal translator. It actually preceded Fortran out into the user space by about 9 months. It was just about done. It occupied 1,998 words on a 2,000-word IBM 650 drum. So there were 2 spaces left and lots of bugs to fix that needed fixing, and they couldn't because they only had 2 spaces left on the drum. But it was a algebraic language, and you could write complex algebraic things in it. I had known about this idea because at the brownstone in the summer at IBM, a guy had come down from the 4th floor of this brownstone to talk to the graduate students and tell them about a new thing that had just hit the scene. They were doing it upstairs. You didn't have to write these CLA for clear and add, and you didn't have to write 005 for add. You could actually write algebraic things, and it was a formula, and there's a program that would translate that formula into machine language, Fortran, and that was John Backus, who had come downstairs to talk to us. So I actually knew about this idea, but Perlis actually had one up and running. So I was able to write a rather complicated, for that time, now it would seem like a freshman undergraduate exercise, but at that time it seemed to be complicated. A simulation of 2 companies engaged in a duopolistic decision-making duel about pricing of cans, aluminum or tin cans in the can industry. And why did I get involved with that? Because if I were going to get a PhD in the Graduate School of Industrial Administration, I sure had to pass some exams. And one of the exams I had to pass, I knew was going to be an exam in economics, which includes micro and macroeconomics. So I figured I better take a course in this. So I was taking a course from Dick Seiert. Seiert was teaching, I think at that time, microeconomics.
Seiert later became president?
Seiert later became president of Carnegie Mellon. And Simon's ideas were blooming, including his earlier papers at Carnegie. They were blooming, including the earlier paper on behavioral theory of rational choice. So and then it was blooming into a model of human decision-making, individual human decision-making and problem-solving. So I needed to do a paper, and I talked to Seyert about what kind of term paper I should do for this course, and we decided to try to do one of these Simon-like satisficing models, search and satisficing models for the decision-making behavior of companies, not just individuals. Mm-hmm. And since that's complicated for lots of companies, let's just do two companies. That's a duopoly. And there were some famous duopolies that economists at the time knew about, where there was data involved in how they behaved, in particular for our thing, pricing behavior. So I did one of those, and of course I stumbled through it, not knowing a lot of economics. Seyert was a very fine advisor, but he quickly got Jim March involved with it, and so the three of us were doing this modeling piece of work. In that case, it led to the first paper that I was actually delivered at a scientific conference. It was in the fall of 1958. Seyert and March asked me if I wanted to deliver the paper on this at the American Economic Association annual meetings in December. So I actually went there and delivered a real professional paper on this piece of work. The piece of work was published in 1959 in the journal Behavioral Science. It had gotten rejected by the American Economic Association journal in 58 because it was about a subject that was not considered to be economics, namely simulation. Simulation was not a way to do economics. By 59, they had already decided to publish a special issue on simulation. So that was the first big programming job I did in non-AI format. Then, go back to the AI question. Remember, IPL1 was a paper language, the language in which the logic theory program of December 15th, 1955 and thereafter was programmed.
That was the computer that thought. That was the thinking machine.
That was the thinking machine that Simon was referring to. Mm-hmm. The logic theorist, essentially the first heuristic program. And Newell and his colleague Cliff Shaw at the Rand Corporation quickly began to implement IPL1 in a real computer. That was the Joniac computer. Joniac computer is actually on display here at the Computer History Museum. They've redone it beautifully.
So what does IPL stand for, and what was it?
Information Processing Language. Mm-hmm. And it was the first language that was dedicated to symbolic manipulation as opposed to numerical calculation. So it didn't use algebra as its metaphor with plus, minus, times, and divide. It used symbols and lists of symbols as its metaphor. In later papers, Newell and Simon actually tried to make more than metaphoric use of this in trying to describe how the human memory would be organized. I'm not sure that was a convincing metaphor, but these languages were oriented toward comparing symbols, organizing them into serial lists, organizing them into, since every list had a symbolic name itself, therefore it was natural to have lists of lists, which of course led immediately to the recursion idea. Programs themselves were symbols, so you could just execute these lists of symbols by throwing the name of the program into the interpreter. It was an interpretive language. You could have things called description lists, which were pairs of attributes and values. The attribute was a symbolic entity, and the value itself didn't need to be one symbolic entity. It could be a list of symbolic entities. So you could have an attribute of color, and then you could have a value, which is a list of the different colors a thing could be, blue or red or purple or something like that. Eventually, the attribute value list idea became very important in not only list processing, but that particular version of it became very important in object-oriented programming.
Now, these ideas, both the logic theory and IPL, both of them made quite a hit at the Dartmouth conference in the summer of '56. Were you involved at all in Newell and Simon's going up there, and what are your recollections about their ideas from that conference?
I was not involved. I didn't know about it. I only heard about it after they got back from actually a pair of conferences, of which the Dartmouth conference was one. They talked a lot about it. I found out then that they had basically taken the logic theorists to the conference with the IPL idea, and they spoke of some of the reactions of some of the other people, particularly Herb Gelernter, who got very excited about this. Herb Gelernter of IBM got very excited about all these ideas and quickly proceeded to implement both a language, which was a list processing language in Fortran, and an application of it to Euclidean geometry. So they talked about that. They also talked about what they thought was a spectacular paper where they gave another paper at a conference of the IEEE, the IEEE Information Theory Proceedings or something, a conference in September of '56, and they heard a spectacular paper by Chomsky, and that was Chomsky's original paper on trying to frame computational linguistics. So the answer is I didn't know anything about it. I had no information prior. Afterward, just a small glow, but nothing more than a few days worth of discussion about it around Carnegie, and then it disappeared into the void.
So here you are, a graduate student in the Graduate School of Industrial Administration at Carnegie Tech. And of course, one of the things that one does as a graduate is settle on research and a dissertation topic. So can you say a little bit about how you decided on what to do about all of that?
I walked into Simon's office. So I got back in September of 1956, start the new year, and I walk into Herb Simon's office, say, I'm here, I have this fellowship, and what do I do? And he opens up an issue of, the current issue of Scientific American, or maybe the issue before last or something like that, and he shows me an article about human learning. It was specifically about human serial learning, and it was about a thing called the serial position effect, and it had to do with the learning of nonsense human syllables, that is, trigrams, which had a vowel in the middle and two consonants on the ends, and otherwise made no sense at all, except that the psychologists had carefully over the decades graded them in terms of meaningfulness.
Were they pronounceable?
Yeah, they're pronounceable. Like the one that I use a lot in my book, in my articles, is DAX, D-A-X, and JIR, J-I-R. But otherwise had no meaning. And there were, it turns out, quite a set of phenomena associated with this part of human psychology called human verbal learning. Verbal meaning word-like things. Especially human nonsense syllable learning. The experiments went back to a guy named Ebbinghaus back in the late 19th century and continued through the particular moment we're talking about, 1956, with massive amounts of results. An article in the Handbook of Experimental Psychology I think by Carl Hovland, famous psychologist from Yale. And Simon said, okay, let's make sense of this. Here's the data. This is elementary learning. We can't ask for anything simpler than this. This doesn't have meaning associated with it. It must have something to do with memory structures. Let's see if we can construct an information processing model, basically as simple as we can, to explain this data. By explain, he meant numerically explain, predict these numbers that the psychologists felt were stabilized numbers. That is, they would talk about them in terms of something like the serial position curve was a real curve. It had real numbers at each end, and it varied with the meaningfulness of the syllables. And
so by explaining it, did he have in mind that the model that explained it would be the model of the way the brain actually does this?
Not the brain. That's a very important thing, Nils, to mention. Never, ever was the brain brought up. This was totally a model of mind, a model of human information processing with symbols at the lowest levels. Now, This shows up in very great elaboration in the 1972 book by Newell and Simon called Human Problem Solving, where they go into great detail about what they call elementary information processes, EIPs. But it also comes up in their Turing Award speech, in which they focus on the level of symbolic manipulation as a level of explanation for what's going on in the mind. And there never was any discussion about brain theory, or even though there were books at the time, like I think it was Ed Berkeley's book called Giant Brains, and the metaphor was running around, but it never cluttered the scientific air at Carnegie. And I've not only lived with that metaphor, I've adopted that. Sorry, not that metaphor. That level of explanation of human problem-solving activity over my whole career. There's now a new book out, and that's become common among most AI, no, I shouldn't say most, what you would call the mainstream of AI thought for 3 decades or so has been at that level of explanation. There has been a bit of work starting in 78 or so where people were looking at what does the brain really do? And they looked at what's a model of a neuron and how do neurons connect, and then came the neural networks approach. But the symbolic processing level of explanation of human intelligence, namely the mind explanation of human intelligence, has dominated. There's a very recent book, for those of you who are watching this 50 years from now, I'm talking about 2007, by Doug Hofstadter, called I Am a Strange Loop, in which his main point is to emphasize the symbolic level of explanation. And he uses as a metaphor or a view that many of us have been using over decades, which is that it's a lot different to explain pressure at in physical terms, let's say, at the macro level, where we do PV equals nRT, then it's a different level of explanation than the statistical mechanics, where you look at individual molecules hitting up against the wall of a container. And that for now, the level of explanation of symbolic manipulation is the right level of explanation. Not that it can't be informed by brain research, but that level of communication between neurophysiological work and psychological work hasn't been, up till now, very productive.
So your work then, after talking with Simon about attempting to build this kind of a model, what happened next?
A model called EPAM-1, which EPAM, incidentally, is the name of a program or a sequence of programs, stands for elementary, perceiver, and memorizer. Hence indicating that we were looking both at the question of how is a symbol perceived, and then how does it, on the basis of that perception, retrieve memories, stored memories. EPAM-1 was a simplistic, back off that. It was a simple model of why the serial position effect, which is the numerical curve that indicates people paying attention to symbols at the ends of lists first rather than the symbols in the middle of the list, and it has a very replicatable shape. What's the mathematical model that predicts that? And also, what's the computer model that is equivalent to that mathematical model that predicts that? That was EPAM-1. But that didn't say anything about the details of the perception and memorization of the individual nonsense syllables. So EPAM-2...
It was more a description and not a simulation?
No, it was a simulation, actually.
And
it and the mathematical... In fact, the appendix to the paper we published in Psychological Review, which is the main theoretical journal of psychology, the appendix to that paper actually gave the mathematical model that predicted the same as the simulation model. The simulation model, I don't remember what language it was written in. I didn't finish my story of the IPLs, I can see, but it may have been written in IPL 2 at the time. I'm not sure. I have to go back to the paper and look.
Ed, let's continue our conversation by going back to talking about the IPL languages. I think you had mentioned something about IPL 1 that was a kind of a paper language. There were actual languages too. So how did that all go?
To actually implement the logic theory program, Newell and Simon and their colleague Shaw at the RAND Corporation did an interpretive language for the Johnny-Ack computer. The Johnny-Ack computer was relatively small amount of memory, I think maybe 4K at the time. And they did a language which was very much, it was symbolic manipulation oriented with lists and list structures and attribute value lists, but it had very much of a serial programming flavor to it, of the typical variety of the path from on which computing had come. And that worked fine. They actually had a running program that proved theorems interestingly in propositional logic. But Newell and Shaw were very dynamic about changing the language and morphing the language into, in other words, they viewed language construction as an area of scientific and engineering discovery. It just wasn't a tool, it was something to look into. And the next thing to look into was IPL 3, which changed the mode rather amazingly. That is, it took an extremum, and that was essentially trying to do everything by nested subroutines and recursion. Now, recursion was possible in the IPL2 structure, but it was not convenient, and you didn't think of it a lot. In IPL3, you didn't think of there was no other way to do it.
Was that the beginning of push-down stacks? Was that?
I don't remember if it was IPL3 or IPL2 that had the first push-down stacks.
Which is basic to recursion.
Yeah, but I think it was in IPL2 because recursion was possible in IPL2. Mm-hmm. But anyway, IPL3 made a big deal of it. That was going to be the central element of this. Well, as with with many experiments, you can push a thing to an extreme and it gets to be awkward, and it's beautiful but not convenient and practical. So IPL3 really was beautiful, but who the heck can make sense of these kind of programs? And you see this whole thing replayed during Lisp. When McCarthy got around to writing a elegant notation for all of this in Lisp, McCarthy's view was, you got to write this out in recursive form. This is exactly why I did it, John would say. And then you got this rebellion about, we can't do this. We can't think that way. We got to have a prog function, which enables us to think serially like a programmer. So you find in the Lisp world, the same tensions going on that went on at the IPL3 days. Well, it came time during all of this IPL3 work to think about a public version of IPLs, because this was all on Johnny-Ack. There was only one Johnny-Ack in the world, and there was a copy of it Johnny-Ack was a copy of the Institute for Advanced Study machine in Princeton, but that was it. So IPL4 got born. And IPL4 was really backing off from IPL3 in the direction of giving the programmer more flexibility. But it was still a programming language. It wasn't like an elegant high-level notation. So I got the job. Newell asked me if I wanted to. I worked in the summer at the RAND Corporation in California, where Newell was still an employee of the RAND Corporation at that time. He hadn't yet taken an offer from Carnegie Tech to be.
So this is while you were a PhD student. You worked at RAND.
Yeah.
In the summers.
In the summers, and Newell asked me if I wanted to be the programmer for IPL4, and sure, that was fun. I was a good programmer.
You were in
So-
the middle of working on EPAM
yeah,
at
I
the
was in the
time?
middle of working on EPAM. And to be part of a project, it was a big deal to this IPL stuff and working with Newell and so on. We actually did the manual first, just so that we wouldn't have a moving target while we were doing the language. We had a crystal clear idea of what we wanted to do, and then
Those are the specs, the manual.
the
essentially.
manual essentially became the specs, but it was actually a manual. It was actually published. It was the first time I ever got my name on the cover of a book. It was Newell, I don't know, Newell, Shaw, Feigenbaum, and Mealy or something like that. George Mealy was a programmer at Bell Labs who did the I/O for the system. I believe this was a 709. I believe by the time we got it done, it was a 709 or 7090 implementation, but I never was very good at I/O. So George Mealy did the I/O, and I did the rest of the programming. And IPL4 became a public language. And then, of course, Lisp was born right around that time, roughly speaking, 1959.
So you were writing EPAM in some combination of IPL2, IPL3, IPL4?
Yeah. And but no, not IPL3. I think I skipped IPL3 because I think it was really hard to program in that language. So back to EPAM. So EPAM 1 was a relatively straightforward model without going into the details of how individual memory items are stored. EPAM 2 dealt with real lists of serial lists of nonsense syllables, and the other favorite paradigm of psychologists, nonsense syllables in associate pairs, where one is called a stimulus and the other is called a response. The order of the associate pairs are randomized for the subject's learning, just so the subject, so you don't confound serial learning with the learning of the pairs. So you might think of serial learning as a degenerate case of stimulus response, and the response becomes a stimulus for the next one, and so on. That's a subcase of paired associate learning. And in trying to, so what makes one nonsense syllable different from another? Well, they have different letters, and what makes one letter different from another is they have different shapes. And if we had a coding of the shapes in a method similar to what the computer vision people would have done 2 or 3 years from then, in the late 50s, early 60s, namely loops and lines and things like that. If we code up the shapes, then we can make a test that tests that one thing is different from another. And if they are different, then let's say these two nonsense syllables have different first letters. And there's, for example, no need to discriminate further if no other nonsense syllables in the list have overlapping first letters. There's no need to make anything more than one test that discriminates some feature of one from some feature of another.
That's how an engineer would do it.
Yeah. So it turns out that, first of all, that was and because we had IPLs, that was the first time that it was absolutely natural to conceptualize that as a growing list structure. You have nothing at the beginning, the memory is not structured at the beginning, and all of a sudden it has a branch.
First
and then that node has a symbol, and that symbol can become a branch, and that symbol can become a branch. It happens that we initially used binary tree. I initially grew binary trees, but binary was not essential. These lists can be more than too long. Mm-hmm. So ternary trees are okay, and n-ary trees are okay. And then at the very bottom of these trees, you actually have the place where you can store the real information about this nonsense syllable, namely the information you need to give it out through the mouth to the experimenter. You have to have it all. You can't just know that the first letter has a loop. You have to actually memorize the material.
Or to the printer if you're building
Or
a
to
program.
the printer, yeah. And memorizing all the material, Simon and I calculated for over a very large number of experiments, done in psychology, it's roughly speaking 30 seconds per nonsense syllable that the subject has to spend on it in repeated trials through the list. If you don't give them 30 seconds, you're going to have to go through another trial and another trial and another trial and another trial.
Until it adds up to that.
Until it adds up to about 30 seconds per nonsense syllable. There's a big difference between recognition and recall, as psychologists knew by that time, knew very well. And of course, in EPAM, the difference is that for recognition, you only have to have as many branches as it takes to discriminate the small number of syllables you have. But for recall, you have to have it all in order to output it. So that was as far as I can tell, that's the first instance in computer science of adaptive growing trees. Now, what I didn't do was to explore that as a subject of scientific discovery. Trees were not interesting to me except as an organization of human memory to model some psychological experiments. To put it another way, Simon and I were sitting there doing EPAM, we were behaving like psychologists. We weren't behaving like computer scientists. Now, on the other side, there was Newell working on what you might say both. He was working on human problem solving, but he was also working, he really sort of had an AI idea in mind, leading to more general things for AI. He also had a list processing idea in mind. But for me, it was psychology, and I was doing my thesis, so I didn't explore trees. Of course, trees became a very important subject in computer science.
Especially these decision trees, as they later were called, in machine learning, right?
Yes. And it would have been good to have some of the early publications in trees. Ed Fredkin at in the BBN or something, not MIT, but I think BBN, also discovered. So Fredkin I think he was at BBN at the time, packaged up this, he also reinvented this idea and put it in another context, and he published a paper on it called Tree Memory. But there were several other computer science-oriented approaches to growing trees that got published in the next several years. But none of those were by me, except insofar as it influenced psychological modeling and early AI. AI people picked up on it because I was publishing in the AI literature, so that was good.
So here we are with EPAM, and it's you're getting toward the end of your graduate career, and EPAM became the main work for your dissertation. Is that right?
Well, that was my dissertation.
That was your dissertation.
Yeah, it started out. It started out at the moment I arrived at the graduate school in September of '56, and it just flowed right through until the point it was time to write it up.
And you wrote it up? And
I wrote it up and took my oral exams. It was a thesis-type exam on the thesis in September of 1959, in the morning of the day that I was supposed to get to New York by the afternoon and get on the USS United States for my Fulbright.
I see. So after your graduate work at Carnegie Tech, and during that time you applied for a Fulbright and ended up getting a Fulbright, or a Fulbright was awarded in some way?
Yeah. So in 1958, I got married, and my wife and I decided that it would be interesting to spend a year in Europe. So at the end of so during that time, I applied for a Fulbright scholarship, which was the only quick way I knew of getting to Europe, was to get a fellowship of some sort to do postdoctoral work. And I didn't know much about where I should go in Europe to do this, but in 1958, the National Physical Laboratory had held what amounts to the first big AI conference, the Mechanization of Thought Processes Conference, in the London area, and so I had the name of the guy who organized that conference.
So the National Physical Laboratory was a unit of the British scientific establishment?
It played the same role in Britain as our National Bureau of Standards did in Washington, now called NIST, National Institutes of Science. What is it? National
Institute of Science and Technology.
Is that what it is? Anyway, it was like the National Bureau of Standards at the time. So it was a government institution. Turing had gone there after the war to follow up on some of his insights into how to build computers and what to do with them. Turing, of course, had died in the early 50s, so by the time I got there in 59, there were still people working on that line of work, and there was still a machine there called the Pilot Ace.
By the way, before going on and talking a little bit about what you did on your Fulbright at National Physical Laboratory, the subject of name Turing came up. Did you read Turing's 1950 paper, and did it have any influence on what you decided to do? This is the paper
yes.
which Turing wrote
Sure.
on computing machinery and intelligence.
I sure did, and so did we all. And its influence was it was nothing like the aha experience of having the actual thing that Simon and Newell were doing, but it was a kind of inspirational that someone was talking about the big picture, and it was very interesting that he was talking about the big picture in the sense of experimental, an empirical approach to intelligent behavior, which is intelligence is as intelligence does, not some big theoretical view of intelligence. So that was shaping.
So back to the Fulbright year. What happened during that year? What sorts of work were you doing?
So in the Fulbright year, I had no reason to expect, honestly speaking, from if I had done a good empirical study, that anything exciting would be going on at the National Physical Laboratory. And indeed, nothing really was. But it turned out that there were other places in Britain where there were very good people pursuing very good ideas, and one of them was, and in Cambridge, I met two such people. They also happened to be husband and wife, Roger Needham and Karen Spark-Jones. Karen was working with Margaret Masterman on computational linguistics. That was a very hot group at the time. There weren't too many of those in the world, and Margaret was a really good leader of that group, and Karen was very young, but she was also very good. Roger was a young person working in what was then called, I believe, the Computation Center. I'm not sure exactly what it was called, but Roger eventually became the professor in that area. But he was interested in the chain of intellectual events and the detail that led to what the Americans were doing in compilers, particularly in the list processing area. He wanted to know more about that. Although we hadn't done a compiler, we had done an interpreter. He wanted to know exactly how that would work. So he was really coming into it from a computer science point of view rather than an AI point of view, which is what Karen was doing. So I met the two of them, and we traded lots of ideas, and they came down to NPL sometimes. I would go up to Cambridge sometimes. It was actually a lot more fun to go to Cambridge because there was a big group of people working up there. That became more or less the best thing that happened on my Fulbright.
Now, wasn't Seymour Papert at NPL
Papert.
around those days?
Yeah, so that's right. There's a sort of a long and funny story involved with me meeting Papert, but I won't waste the time out here to tell that funny story. But Papert showed up exactly at the same time that I was showing up, from South Africa, via Europe, to the National Physical Lab. Papert was a leading mathematician in South Africa. I think I once, and Papert's wife, who he was not living with at the time, but whom I met several times, it was said that she was South Africa's second best mathematician and Papert was South Africa's fifth best mathematician. And Papert had, so he was really a mathematician, but he had been interested in complex models of behavior. So he went to Europe to work on that with, I believe, with Piaget. He spent some time, and I believe, and when I knew him, he had just come out of experimental work with a psychologist named Curler, who worked on perception in the situation where the perceiver has been wearing eyeglasses that change the world, like upside down or right-left confusion. And indeed, it led to some hairy episodes with driving with Papert in London, when he would drive into a roundabout and he would have to stop and think about whether he was going to go left or right and what indeed was left.
So then while you were in England, you were probably thinking a little bit about, okay, what do I do next? And what kind of career do I have?
Yeah, I already had a job. Before I left Carnegie, in typical fashion, as we know today even, if you're the supervisor of a graduate student, one of your responsibilities is to help place the graduate student in a proper job, hopefully academic job, down somewhere. And since I was working with Herb Simon on basically psychology, I was a card-carrying psychologist, member of the American Psychological Association. It seemed reasonable to go to a place that had a really good psychology department and was doing sort of cutting-edge work in modeling, psychological modeling, and that was Stanford University. Dick Atkinson was here, Pat Suppies was here, Gordon Bauer was at Stanford. So Herb approached Pat Suppies to try to get an in for me to get a job, and basically the answer was no.
They weren't hiring that year.
Or maybe they didn't want to hire in computer simulation, or maybe Pat didn't like the work, or whatever. I've mentioned this numerous times to Pat, and he chuckles all the time, doesn't remember any of this. But where it was easy to get a job was in a school of business administration, because that's where I had a union card, and a union card signed by one of the best in the area, namely Herb Simon. So that turned out to be, I had wanted to come to the West Coast, particularly to the San Francisco area. So Berkeley was excited about getting me and about getting Julian Feldman. Both of us left Carnegie at roughly the same time. Julian got to Berkeley a year before I did, because I went on a Fulbright. And I got there in September of 1960, and then the two of us started to teach essentially two things. One was organization theory a la March and Simon, which we both knew from our graduate work, and this new discipline called artificial intelligence, or in some variations of it, computer simulation of cognitive processes. We were teaching that to Berkeley students in 61 and 62. That's when we were having a lot of trouble getting, what would we do? There were no books on the subject. But there were some excellent papers, and we would send the kids over to the library, and we'd have photocopies of the papers. I don't even know if Xerox machines existed at the time, but we had photocopies of the papers. Thermofax or something. And we just decided that we needed to do a collection. It wasn't just our students who were interested in this. There was a whole nation, or maybe a international need for such a thing. So we took the papers that we had collected up, plus a few more that we asked people to write, and put together a collection called Computers and Thought, published in 1963. Interesting story about that is, tried to get it published. Herb Simon happened to be the business publications editor for Prentice Hall. So, of course, we went to Herb and said, Herb, here's this book. He said, he advised Prentice Hall not to publish it because it wouldn't sell enough copies. He later told me that was one of the big mistakes of his career, but it did sell a lot of copies. It was, and it really helped to. There were, as I say, there weren't very many books in AI at the time, so it really helped to launch the field.
It had papers both in cognitive science and in what later became more AI, right?
That's what we decided to do. And maybe, I don't think we sort of made that up. I think that was a kind of a thing that was going on in the culture at the time. Namely, there were a group of people who were behaving like psychologists and thinking of their work as computer models of cognitive processes, using simulation as a technique. And there were other people who were interested in the problem of making smart machines, whether or not the processes were like what people were doing. The kind of sentence that went around, and lots of us used it, and I notice it's still being used routinely, is we don't make airplanes by modeling the wings, the feathered wings of birds that flip up and down. We have, for engineering purposes, we have different kinds of wings.
But right about that time, maybe in the late 50s, the phrase cognitive science first appeared, didn't it? People were actually thinking of the discipline called cognitive science.
Boy. Let me give you my impression of that, but I could be very wrong. And I'm not a history buff in that sense, like you are. It's my impression that the phrase being used at that time was cognitive psychology, not cognitive science. And that the people that were practicing the simulation art were using the term information processing models. In fact, I think Newell and Simon's working paper series had that kind of a phrasing to it. They weren't called computer simulation of cognition working paper or AI working paper. They were called something like information processing working papers. It's my impression that the term cognitive science arose when, in the late 70s, the AI community was trying to get organized into a society, as opposed to the confusion that everyone doing their own thing confusion.
I think you're right about that.
And that I was strongly arguing that the term artificial intelligence really wasn't the right term to use, because it just hit the wrong nerve in the public at large. It gave some hint of hubris, and anyway, who wants something that's artificial? So I had been proposing that we, AI people, change our name to cognitive science. Well, which makes a lot of sense. That's what we do. Well, that really got people upset in that other community, that cognitive psychology community. Examples being Don Norman as being one of the people who got upset. But there was a whole bunch of, I think Roger Schenck may have been another one. But they quickly assembled themselves into a thing called the Cognitive Science Society. And having sort of sewn up that name, that was something then we couldn't use for what society we were trying to form.
They had a founding meeting, I think, didn't they, in San Diego or
Yeah.
maybe UCLA in 1979 or 80, something
Yeah.
like that.
And it was 79. In August of 79 was when the group that had been working on the AI Society, which ended up being the American Association for Artificial Intelligence, AAAI, met in August of 79 at the IJCAI Tokyo meeting to plan our next step, what we were actually going to do. And then Newell was asked to be the first president of the new society. I was asked to be the second president. Raj Reddy was the was really organizing the whole thing. And by that time, the cognitive science people had actually incorporated as the Cognitive Science Society. And indeed, they did have their first meeting about the same time that AAAI was having its first meeting.
Now, back to computers and thought for a moment. You and Julian did a very generous thing, I think, with the royalties there. Do you want to say something about that?
Oh, that worked out wonderfully. So we were in a situation where we had many, many papers, maybe 20, from different people, and we didn't. How would we distribute the royalties? We didn't know that the book was going to sell many copies anyway. Herb Simons certainly thought it wasn't going to. And what we were going to distribute the royalties in dribs and drabs to individuals. So we just wrote to everyone and said, how about if we just set up a prize with these royalties? And we'll call it the Computers and Thought Award. And it was a prize for young people, not like we see these days where the older, more mature people who have had a long career get big prizes toward the end of their career. This would be for like the best thesis of the year in AI, or if not the thesis, then of the best contribution of a very young person and in the maybe first years of their academic career. So that was the Computers and Thought Award, and I don't know exactly when IJCAI came into existence, but we put it in the hands of IJCAI, to International Joint Conference on Artificial Intelligence, which was just popping up around that time, to make the award and give out the award at their biannual conference.
Now, back to research at Berkeley. So we've talked a little bit about your teaching a course and putting together this collection of papers in computers and thought. How was your research life going during those days at Berkeley?
It was, I would say, very frustrating for actually several reasons, but the ones that jump to mind are, first of all, it does matter what department you're in a university, and it's not a casual matter. If you are a professor in the School of Business Administration, you're going to get the PhD students that come by that graduate school. And if you're not in the place where computer science, what we would now think of as the right kind of person for computer science, or even psychology, if you're not in that place, they're not going to flow by you. And I was not in the psychology department. I was a member of the thing called the Center for Human Learning, which had its own frustrations, which I'll tell you about in a minute. But I didn't get that flow of graduate students. I didn't get the flow of graduate students that were coming by Harry Husky in EE, and I didn't get the ones that were coming by the mathematics department-oriented computer science students. Berkeley was a big mess at the time in terms of where computer science was located. They eventually ended up with 2 departments, which had to be then later welded into 1 department. But I didn't get any of those graduate students. So that was a problem. I had not a very good set of graduate students. Secondly, I was really not very happy doing models in psychology. It was great to do a thesis in that area because I had both the interest and the support of Herb Simon as I was doing it, and I learned a great deal. But at the very heart of things, I was really interested in artificial intelligence, not in exactly how to model the results and how exactly to formulate models that would replicate the results of particular kinds of psychological experiments. In other words, I wasn't too interested in my union card in psychology. I really liked AI.
You didn't want to be constrained by having to have feathers on the wings.
Yes, and in the culture that I came from, the feathers on the wings were taken very seriously. If you look at Newell and Simon's book, Human Problem Solving, you will see hundreds of pages of direct matching of what GPS was able to do with exactly what human protocols were doing in the same experiment. Mm-hmm. Newell and Simon took that stuff really seriously. And similarly with the EPAM work, we took that really seriously. And I was not interested in doing the psychological research myself to validate certain aspects of EPAM. The Center for Human Learning at Berkeley was not interested in doing it. They were very experimental people, but they were not interested in anybody's particular theory. They were interested in 82 variations of the same experiment by turning the knobs in all these different directions, and that was very discouraging.
Yeah, you did finish EPAM. Didn't you do
Yeah,
another version of EPAM?
I did another version of EPAM, long distance with Herb Simon, EPAM 3. We had a bunch of things to pursue at the end of my thesis. Every thesis is that way. It leaves open questions. You want to finish them off. We did that. We published a paper in, I think, 1965 about EPAM 3. I think I wrote a couple survey-ish kind of articles which summarized all of that research, and then essentially I got out of that field. And Herb stayed with it. Herb was publishing EPAM papers right up until the time he died, back in the early years of the century. I don't remember exactly, 2002 or something like that, but he was publishing papers right up on EPAM right up until that time, and he went through various versions of EPAM with a student of his, Howard Richmond. I think they may have gone up through EPAM 7 or 8 or 9 in various variations of the model. And I did occasionally publish a paper with Herb along the way, maybe one per decade, on some aspect of EPAM that Herb was interested in and invited me to be a co-author on. But essentially I gave that up.
Now, did you have research support when you were at Berkeley?
Yeah, I did.
Have some research contracts?
Initially, I got a foundation grant. And I'm blocking on the name of what foundation it was, but it was a relatively small grant, but it was enough to keep Julian and me going. And it came with no government strings attached. Herb Simon had recommended to a foundation that was beginning to make grants in this area that we were good people to give money to. Then we had a wonderful event, which is that J.C.R. Licklider came by. He had taken over, he had started a new office for ARPA, not DARPA at the time, ARPA, Advanced Research Projects Agency, in information processing techniques. He had picked up the word that there were some good people at Berkeley in AI, but also some good computing people at Berkeley, Harry Husky in particular, a pioneer in computer architecture. So he came out to discuss ARPA contracts. We weren't, of course, the only ones. He was doing a big one at MIT with Project Mac, and a big one at Carnegie Tech, or maybe Carnegie Mellon by that time, called a Center of Excellence grant for the work that Newell and Simon and Perlis were doing. At Stanford, he was interested in funding John McCarthy. I believe he was funding John for AI work, not time-sharing work, but I'm not positive of that. But at Berkeley, he wanted Julian and myself to do AI work, and he wanted Harry Husky and a double E team to build a medium-sized time-sharing system, which we eventually did. So I was co-PI of a contract that had two branches. It had one branch doing EPAM and other related AI things that I might be interested in. Not too definite, because you didn't have to be very definite with ARPA at that time. And another branch that was supposed to do something halfway between the PDP-1 type time-sharing system that McCarthy had pioneered and the Project Mac time-sharing system, which was huge, that they were doing at MIT. That was actually a very, very interesting experience, not on the AI side, but on the computer side, because Harry Husky took a sabbatical in India, and the guy who substituted for him as PI was a superb computer engineer, Dave Evans, the designer of some of the Bendix early computers and later co-founder of Evans and Sutherland. And I really learned a heck of a lot about how computers are designed from Dave as we were selecting a machine to modify that would become the, later on it would become the SDS 940 time-sharing system. And it would, but anyway, that was the grant support that I had.
Mm-hmm. So Ed, we had talked about you and Harry Husky having the first ARPA grant at Berkeley, and under that grant you had done some work finishing EPAM 3. What sort of intellectual ideas were you interested in at that time?
The I was in, actually, it was for me, it was a period of kind of an intellectual turmoil, or a searching, or a lack of direction, because I hadn't quite settled on yet where I wanted to go. I had pretty much decided that I wasn't going to go down the psychology route. And as I mentioned, I mentioned that I was more interested in building intelligent machines than in the building models that had a great verisimilitude with the human data that the psychologists had. But when I look back on it, I have a feeling that it was not that bland. I had a feeling that there was a much deeper component to it. And I only get this feeling looking back in time that that for reasons that are not totally clear to me, I really, really wanted smart machines. Or I should put it the really in another place. I really wanted really smart machines.
Super smart machines.
Yeah. And I had been, I remember very clearly a paper by I.J. Good on the ultra-intelligent computer. And yes, in fact, I.J. Good, I think, published two versions of it, one in '56 and one maybe in the early '60s. But yes, that's what I wanted, the ultra-intelligent computer. And I wasn't going to get there by either walking down the road that I was doing with EPAMs, which is models of verbal learning, or doing what I then considered wonderfully inventive puzzle-solving tasks, like Newell's. He was doing trigonometric identities. He was
cryptarithmetic.
Cryptarithmetic, yeah, those kind of things. Donald plus Gerald equals Robert. Oh, you know, come on, that really is not it. That's not where we're going. Well, for him, that was where we're going, because he was interested in detailed models of human thinking about problems like that.
Solve those problems.
But I wanted really big stuff. So big fish. You had a name for it recently in one of your papers, going after the dream or something like that. What was it called?
Eye on the prize.
Eye on the prize, yeah, eye on the prize. So yeah, the big idea. And for Newell and Simon, the big idea was to do the best psychological models that had ever been done. And in fact, they both did win the equivalent of the Turing Award in the American Psychological Association, as well as winning the Turing Award. So they succeeded, but at least in recognition. But I wanted something bigger, and when I thought of something bigger, I couldn't think of anything bigger in the, and I really still can't, than induction. That is, induction is what we are doing almost every moment of almost all the time. We're
both informally and as scientists.
Yeah, that's right. I'm thinking, at that time, I was thinking informally. That is, we're taking in a lot of data, and we're building a model of the world.
Making theories.
And we're constantly testing that model of the world and revising it. And so I wrote a couple paragraphs on this, which end up being that were the end of the introduction to computers and thought. Not a section introduction, but the main introduction was about induction and why I thought that was the way we were going. That's what was going to carry forward into the future. But I didn't have a real, so that maybe that's a good strategic plan, but it wasn't a tactical plan. I didn't have any plan for how to do it, and I thought hard about it. And during those years you were talking about, I was kind of in the middle of thinking about it. I had thought and picked up several what Newell and Simon would call task environments, and had rejected them for one reason or another as not being the right ones.
So what's a task environment again?
Yeah. It's a sandbox in which to specifically work out your ideas. So it's a domain in which you can experiment, you have actual problems, you have actual knowledge, you have actual procedures that can work in that domain. So, for example, for Newell and Simon, it started out being propositional calculus. The next one was chess. For GPS, they chose
Lots of puzzles.
Lots of puzzles. So those would and throughout AI, Galerter had the geometry theorem prover. Jim Slagle had calculus. Everybody had some task domain in which they were working. And I think it's very important to emphasize to this generation and every other generation of AI researchers how important experimental AI is. AI is not much of a theoretical discipline. It needs to work in specific task environments. I used to tell McCarthy and others, I think I may have even written it down, that I'm much better at discovering than inventing. And if you're in an experimental environment, you put yourself in the situation where you can discover things about AI. You don't have to create them de novo out of your head. I have a feeling that my colleague John McCarthy is more of an inventor than he is a discoverer. He doesn't play around with his ideas a lot in experimental task domains. So, but I'm from the experimental AI school. So I was looking for a task environment or a complex sandbox in which to play with, to discover induction methods, induction ideas, induction problem solving. And it had occurred to me that, well, let's see, how did it had occurred to me that scientists were a good place to look. The reason is that if you look back at, let's say, the early chess machines, Simon spent a heck of a lot of time examining books on chess, openings, end games, tactics for the middle game. Alex Bernstein, who worked on one of the early chess programs, was himself a chess master. That seemed like that we in AI were respecting expertise in those areas. So who are the experts in induction? Well, scientists get paid to do that, or at least according to the stereotypic model, they get paid to do that. They have a lot of data, laboratory data, they form hypotheses, they make predictions, they revise their hypotheses.
So the forming hypotheses part was what you were interested in.
That's right. And actually, theory formation, I don't want to go into the difference right now between what I was regarding as hypothesis formation and theory formation, but theory formation was the next step along the inductive process. So I happened to be saying this, expressing it during conversations at Saturday morning sessions being run by a Stanford professor in psychology, Carl Pribram, at the Center for Advanced Study in the Behavioral Sciences, and it was on basically minds and machines, what we would now call minds and machines. I don't know what Carl called it at the time, but
How did you happen to find out about that and go down
I
there?
have no idea. It's just, I was at Berkeley. It was happening at Stanford. It's a local, it's relatively, maybe I was just in touch with Carl. In fact, I think I was, because Carl was running that's right, Carl was running a series of annual workshops sponsored by the New York Academy of Sciences being held at Princeton called Remembering, Learning, and Forgetting. And Carl Pribram was intrigued with EPAM. So he had invited me to a series of these things. So I was in touch with Carl Pribram. So it must have been directly through Carl that I found out about this. And drove down the old Bayshore Freeway, the 2 lanes on each side thing. And one of the other people who showed up there, because he just was interested in the topic, but I have no idea how he knew about it, was Joshua Lederberg. Maybe McCarthy told him about it. But Josh showed up because he was being reintroduced to computers from, in the early days of his scientific career, he had been involved with computers from a card punch calculator point of view, and now he was learning the Burroughs machine, learning Algol from Forsyth. He wanted to test his knowledge out on some complex problems, so he was writing an algorithm that elucidated chemical structures, and he was working on a mass spectrometer project he was working on an entire instrumentation platform that would fly to Mars and
Look for life, huh?
look for life. So I was mentioning this to Josh, and he got interested in the subject, and I told him that by that time I think I had decided, or at least I was in the process of deciding to go to Stanford. Maybe I already decided. And Josh said to get in touch with him and we'll work on it. So I did. First thing I did when I got to Stanford was, other than find my way to the bathroom, was to go talk to Josh about this. And Josh had a specific suggestion. When I told him exactly what I wanted about the induction process, it wasn't any old scientific reasoning I was interested in. He said, yeah, I have just the one for you, and we're working on it in our lab. His lab was taking the mass spectra, doing the mass spectrometry of amino acids, because they were their planet probe was going to look for amino acids as part of the method for discovering whether lifelike forms existed on Mars. So the question was, how do you go from looking at a spectrum of an amino acid to the actual structure of the amino acid, the chemical structure of the amino acid? And that's how we started in with the Dendral project. We used, I was good at heuristic search. He had an algorithm which was good at space generation, namely something like, I suppose there's a guy who's good at mastering chess because he knows thousands of good things to do on a chessboard, but you still have to have the rule the move generating algorithm.
So he had the legal move generator.
He had the legal move generator.
And you thought you could come up with the heuristics.
Yeah, so the legal move generator was called Dendral, and the AI program was called heuristic Dendral.
Now, when you left Berkeley to go to Stanford, how did that go? Did Berkeley try to keep you? Stanford tried to hire you? How did that work out?
Good question. Okay, so I've already told you that being a professor, untenured or tenured, in a business school wasn't really quite the happiest environment for a person who had the kind of goals I had and interests. But in any case, some tenure is better than none. And Berkeley's a really nice place, and we had a beautiful house in the hills. And so Berkeley started in, believe it or not, quite early in my career. They started in on this tenure process. I say quite early because I got there in 1960, but they started in on this tenure process from in the 63 through 64 year, because they had given me an acceleration at the front end of my assistant professorship in order to get the salary level up right. In the Berkeley, University of California system, the two are locked together. So, or at least that time they were. So I was being evaluated for tenure a little bit early, and the business school really couldn't quite make up its mind as to whether it wanted this weird guy who basically talked about artificial intelligence. What's that? It's not accounting, it's not marketing, it's not finance.
Yeah.
So that kind of opened up my thoughts to, it's not easy to open up your thoughts to searching around when you're you bought this beautiful house in the hills and you're settled in and all that. But I began to search around, and I must have made it known to McCarthy that I was doing that, because John took the idea to Forsyth. In fact, I think with a very positive recommendation, said, let's hire him. And Forsyth said, great, let's hire him.
Those were the days when you could do it that easily.
Yeah, and there was similar thing went on with Klaus Wirth. Klaus was Harry Huskey's. Harry Huskey was Klaus's main advisor, but I was an advisor on Klaus's thesis as well, so I knew Klaus Wirth, and then George hired Klaus to come down as an assistant professor in '64. I was off on a sabbatical or something in the last semester, the September through December period in '64. I traveled to Russia as a guest of the Academy of Sciences, and then got back to Berkeley during all the turmoil with the free speech movement and Mario Savio and all that. Anyway, left on December 31st, came to Stanford on January 1st.
Now, you left someone at Berkeley who was probably a little bit
so,
disappointed.
So I had this money, and we were going to build an AI group. And so I was hiring the best AIers I could get, and one of the best was one of Minsky's students, Bert Raphael, terrific guy. And by the time Bert actually showed up in Berkeley, in fact, he showed up not only as a research staffer in AI at Berkeley, but also rented my house while I was off in Russia, he and Ann. And but I was leaving, so that was not a great thing. I mean, Bert made a career move, and then it turned out there wasn't any AI at Berkeley except for me and Julian. And Julian was going to Irvine, and I was going to Stanford. So
there was Bert, high and dry.
So there was Bert comes down to SRI, and
good for us.
Good for SRI.
By the way, when he wanted teaching it, he was teaching us how to do list programming. He insisted that we use recursion. No progs were allowed.
Where did you get that?
Huh? When he was at SRI.
Oh, when he was at SRI.
Teaching us about.
I see.
About Lisp. Had to be recursion. And one of the guys who was trying to learn Lisp at the time thought, aha, this is like programming underwater. You need scuba gear. Anyway, so now you're at Stanford.
I'm at Stanford. Josh and I kind of framed up this project, what we were going to do, and I did a working paper with Dick Watson, who was another student of mine at Berkeley. I had been on his thesis committee. He was another system engineering guy, but he wanted to work in AI. Had decided. Came down to Stanford. Left soon thereafter. He never really...
He went to SRI, didn't he?
Went to SRI, and then Livermore, I think. But Dick and I wrote a paper called Opportunities for Graduate Research, and it laid out... This is the first paper ever published in the Dendral project, but it was a kind of a overall glossy view of the Dendral project. And as a result, we didn't get any doctoral students who were interested in doing that. That's a good story in itself as to why doctoral students in AI or computer science shy away from things like that. But we did get 2 master's students, one of whom you know very well because she worked at SRI later, Georgia Sutherland, absolutely fabulous knowledge engineer.
Yeah, excellent.
And Bill White, also terrific. So we got these 2 wonderful master's students to work on the project. And in a way, that was way better than getting PhD students because Georgia and Bill were totally dedicated to the idea of getting these programs running, and as opposed to graduates, PhD students who kind of wander all over the map.
They would have wanted to do their own thing.
Yeah.
And then so what computer were you using?
We started out using the PDP, whatever PDP John had at the AI lab, PDP 6 at the time, maybe it morphed into a PDP 10 at some point. We started using that and using it under time sharing. And we ran into some problems there. So we moved, I'll tell you what they were, but we moved back onto campus using the IBM 360.
So you were out at the AI lab on?
Well, Bruce was. Bruce Buchanan.
Arrastradero.
Yeah. We would do that was like our office. On campus we had our sort of thinking office with Lederberg and myself, but the actual experimental work was going on terminals of in Stanford AI lab. And
on Arrastradero Road out there.
Arrastradero Road, yeah. And the problems there were partly that the machine, it was just a wonderful time-sharing system, one of the best in the world at the time. And therefore, it was tremendously overloaded. Everyone wanted to use it, number one. Number two is, one of the people who wanted to use it the most was John Chowning, inventing these FM synthesis ideas for computer music.
Which made a lot of money for Stanford.
It made a huge amount of money for Stanford, but you can't believe how much computer resources that soaked up. And so John was on it all the time, heavily loading the machine. The other thing was Jerry Feldman was doing the Sail language, and that was heavily loading up the machine. Plus there was robotic experiments and other things going on. So
and then they take the machine down every now and then.
Well, that's normal, yeah. So, and then the other problem was that we were working with chemists doing what later was called knowledge engineering, or knowledge mining out of the heads of these professionals, these experts. And they would have a long drive to, like Alan Duffield we were working with, he'd have to drive from the chemistry department down here on campus all the way out to Arrastradero Road. That's about a 20-minute drive, 20 minutes back, and things would have to be very scheduled in order to do that. So we decided to move down to campus, and that means that we needed extra money in our budget to buy computer time at the 360 Computation Center. But DARPA was very nice about that, and they said, okay, sure, if that's the way you have to do it. So we had a semi-interactive experience, it's sort of a remote job submission by terminal experience.
Now that was, so Lick, was that Lick Lighter at that time? Probably, huh? Maybe
no, Ivan Sutherland had taken over, and then Bob Taylor. So it was not Lick. Lick was already gone.
Okay.
But things were still wonderful at DARPA. I mean, Ivan and Bob couldn't have been better. And they didn't ask nobody asked us in any respect at all, not even detail, whether the stuff we were doing in mass spectrometry had anything to do with the military, or they didn't even ask in any detail what it had to do with AI. If you thought it was a good idea, we'll do it.
We're sponsoring good ideas. That's what we do here.
Yeah, that's what we do here. And at Carnegie Mellon, it was called Center of Excellence. They didn't even have to tell them what they were doing with the money. They were just being excellent. So we moved back onto campus, to answer your question. So then, as things matured, and we were really, by a little bit later on, Lederberg and I were participating. He was PI and I was director of the project, building a computer center for the medical school, which was called ACME, a computer for medical research. ACME was an excellent time-sharing system for its time. It was designed by Geo Wiederhold. But ACME had its day in the sun. And by the time ACME was ready to essentially to fold up as a project, either the medical school would support it or it wouldn't, but NIH had paid for its development, and they were going to move on. We moved on to say, okay, what we need is now a computer center for biomedical AI, which included the Dendral project, but it also included the work that we were starting to do with the doctors on mycin, and other medically related investigations we were doing. And we also wanted to enliven a national community of interest who didn't have time sharing, but who did have access to through Licklider's good offices, they had access to the ARPA net. So through tips at their location. So we applied to NIH for money to get a computing machine to do all this. Well, what was a computing machine? It was basically the same as McCarthy had, except eventually we just wanted to use the 10X operating system. I think we used TOPS 10 or TOPS 20 at the beginning. McCarthy was using some other operating system, but basically the same machine.
So now,
was SUMEX.
there was a time when you were using the Q32.
Oh, yeah.
Was
that was Licklider's doing.
Was that, so that was while you were doing the Dendral work?
It was right at the beginning. As soon as I got to Stanford, Licklider was still in office. He had sponsored he had paid for, so his big projects were Project Mac on the East Coast and converting an air defense computer called the ANFSQ-32 at System Development Corporation.
That had come from Lincoln Labs initially, or maybe not?
It was one of the prototype machines for an upgrade of the SAGE system, I believe.
Okay.
And SDC was programming the software for the SAGE system. So this computer was now surplus or something. He wanted it converted into a time-sharing system and got SDC, well, paid SDC to do it. But there had to be a user community. So he kind of strong-armed a bunch of us to be users of that Q32. Well, it turned out in our case, it was okay. I strong-armed a psychology graduate student that was working with Gordon Bauer and myself, John Anderson, to use that as the means of writing his thesis HAM, Human Associative Memory, which is another kind of memory model similar to EPAM, but more extensive. And he did it on the Q32 in a little converted closet up in Sarah House, that old building that we.
So your work on the Q32 then was before you used the PDB-6 at the AI lab, or overlapped?
Well, they overlapped, but Dendral was not running on the Q32. If I remember right, it was only Anderson's work, I think.
I see.
I could be wrong.
Okay.
Georgia Sutherland would know.
Well, now, so with Dendral, before we get on to the business about the big computer for the medical center and that community, with the Dendral work, sometime during this time, Bruce Buchanan came to Buchanan. How did that come about?
Bruce was a student in the philosophy department at Michigan State, particularly doing philosophy of science work as a PhD candidate. He was working on, to use words that came out of the title of his thesis, the logics of scientific discovery. Those words were the kind of words, I didn't think of them, but they were the kind of words that could have described exactly what was on my mind in '64 when I was thinking about this, talking to Lederberg at the Preber meetings and so on. Gee, isn't that a wonderful way to express it? Bruce had read writings of Newell, Shaw and Simon, and had realized that these had emerged as Rand Corporation publications. And Bruce needed a job in the summer, so he wrote to Paul Armour, the head of the department. Wasn't called computer science, it was called numerical analysis department, but he wrote to Rand, and said, do you have a summer job for me? And Paul sent it on to me and said, do you want this guy for the summer? And when I looked at what he was doing, I said, sure, that looks like it's great. Couldn't be better. So hired Bruce in the summer of '64, and we exchanged a lot of ideas about scientific discovery and how you would model it. Then Bruce needed a job when he finished his thesis in the spring of '65. So Bruce wanted a letter of recommendation to get an assistant professorship in philosophy somewhere. And I said, Bruce, you don't want to do that. We have this wonderful project that's just exactly described by your thesis, Logics of Scientific Discovery. And I told him about it, and we arranged for that. We were actually in a bridge period, bridging off of some funding that we got from NASA, which happened to be located in Berkeley. So Bruce showed up at Berkeley for a while to kind of satisfy that bridge obligation. And then in 1966, 1 year later, he made the transition to Stanford and started work on the campus.
Got right involved with the Dendral project.
Yeah. Well, he was working on the Dendral project all along. It's just that he...
Now he was doing it at
Yeah.
Stanford. Why don't you tell me a little bit about Dendral? What it was really trying to do, some of the techniques you used in
Okay.
having it do what it did?
Yeah. So the first thing I got to say, I will tell you in AI terms, try to keep it short, use AI terms as a shorthand, which maybe not too good for people way out in the future there who don't know these AI terms, but what can I do except point you to references, lots of things, like a book on the Dendral project published by McGraw-Hill, Robert Lindsay, Buchanan, myself, Lederberg, I think are the main authors, published in the 70s. But I want to start out by saying that we did not have a grandiose vision. This was bottom up. This was really bottom up. We started with the Dendral algorithm, which was the legal move generator. And we started generating some chemical molecules that contained carbon atoms, hydrogen atoms.
So these chemical molecules that you generated, these were in the form of what, sort of graphs? Little
Chemical graphs.
Chemical graphs
But
with atoms and the nodes and
topology,
links.
but not geometry. We just didn't deal with 3D geometry and never did. So it was all connectivity.
Like the graphs you might see in a chemistry course.
Yeah. And carbon has a valence of 4, so it's a 4-connected thing, and oxygen is a 2-connected thing, and hydrogen is a 1-connected thing. So we started out with the Dendral algorithm, and one of the interesting things that we discovered almost on day 2 of the project was, or not literally, but let's say just after we got Lederberg's algorithm running in Lisp and ran off a few tests, was that even for the second simplest amino acid, threonine, there were structural isomers of threonine that we generated simply, and there were only 32 of them, I think the number was, and therefore it's not a big deal. But a whole bunch of them were not present in the Beilstein Handbook of Known Organic Structures. The reason is no one ever thought of them. No one ever thought of...
They were structurally possible.
They were makeable by any graduate student in any laboratory. No one had done it. It was not in the Beilstein Handbook. So that was an interesting thought, that even without intelligence, we were able to, quote, discover, unquote, some things that weren't in the literature. But then the spaces, I said threonine, second simplest amino acid, was 32 things. But as soon as you start adding some more carbon atoms with branching factor of 4 and some more nitrogens with 3 and so on, you start adding atoms, you start getting up into huge spaces. Well, AI people are comfortable with huge spaces.
Huge meaning what, tens of thousands?
No, not tens of thousands. 10 to the something or other. Huge.
Huge.
Exponential, big spaces. But that doesn't scare AI people. AI people come out of a background where legal moves in chess are 10 to the 120th for a game, roughly speaking, plus or minus a few orders of magnitude, maybe 10 orders of magnitude. So we know what to do with that. What we do is we prune the space, and we steer our search through the space. So that's what we began to look for. How can you prune? How can you steer? Well, you want to the pruning and steering, to make a long story short, comes from knowing a lot about chemistry. And you can either know about chemistry in general, like, for example, if you string out two oxygens together, you're going to make a peroxide. And peroxides are just inherently unstable. So you'll blow up the instrument if you do that. So if you start juggling these atoms in the structures, if you get an oxygen connected to an oxygen, don't bother.
Throw it out.
Throw it out.
The machine would have blown up, and it didn't blow up, so
that's right,
throw it
exactly.
out.
And so what you do is you get rid of not just that one, you get rid of a whole subtree, just like you do in chess. And then the other has to do with knowledge that's specific to the empirical discipline of mass spectrometry. Some things break up in certain ways and not in other ways, and you got data, and the data can be used to...
And chemists know how they break up.
Our chemists did. Our chemists were... that's another interesting story. Our chemists were Carl Djerassi, a famous man, inventor of the chemical behind the birth control pill. Later, one of the world's most respected mass spectrometrists, which is the phase he was in when we knew him. He was also doing commercial adventures along the side. He was the CEO, I think he was the founding CEO of Syntex, or close to it, maybe the CEO when Syntex moved to Palo Alto, to Stanford Industrial Park. And then he started another company, and anyway, Renaissance guy. But he was a leading mass spectrometrist at the time, and the author, or the editor, of a big handbook of empirical mass spectrometry. What I mean, it's not theoretical, not looking at the quantum theory and deciding what will break inside an atom, but looking at what did break when you bombarded these things. So Carl and his team knew a huge amount about mass spectrometry. And when we began to show them by deliberate strategy, we began to show them the early, when I say them, I mean Carl particularly, the early, quote, results, unquote, by which I mean really poor results, by intention. We didn't want to make this very good. We wanted to show Carl something really poor. And Carl would say, that is really stupid. And our answer would, already planned, is, Carl, what is it you know about mass spectrometry that we don't?
Yeah.
That was it. So we got Carl to work. Carl got hooked on the project. And he laid out a series of what you might call knowledge adventures, or maybe he opened up the minds in different, maybe that's a better metaphor, for ketones and ethers and sulfur-bearing compounds, and there's a whole bunch of them that he laid out for us, and we systematically worked our way through that while elaborating the underlying AI method, which was simply a generate and test method. It was generate and test with a prediction. We had a thing called a predictor, which would predict for those molecules that passed the test what mass spectra would result from those molecules, and what did we actually have.
Oh, you had a model of what the mass spectrogram would do.
That's right. We had a virtual mass spectrometer. So
now, were these during the days in which Dendral was only handling the acyclic?
yes. So all of this was acyclic molecules. The original Dendral algorithm by Lederberg was a tree-generating algorithm, and cycles were really hard because cycles brought in all kinds of mathematics that we didn't know.
Cycle, like, for example, a benzene ring would be a cycle.
Yeah, that's right. Closed rings. So computer scientists or were at the time pretty good at tree structures, pretty bad at cyclic graphs, although there were a few people that were great at it, like Bob Targent, who was on the faculty here. Then now the discipline is way ahead of where it was then. But we actually hired a mathematician on sabbatical at the time, but he liked the project so much he just stayed. That was Harold Brown, from tenured professor at Ohio State. Came and worked with us, and along with some graduate students, Larry Mazinter, and a couple other graduate students, and Georgia Sutherland doing the programming, we worked out the cyclic generation strategy. Now, Georgia actually did one that was, well, let me go back. The Lederberg acyclic algorithm was generated the space completely but irredundantly. And that's magnificent. That says that every candidate that could possibly be in that space was in that space, and it never occurred twice. So Georgia did one for cyclic molecules, which didn't have that nice property. We could accidentally ignore some, and we could accidentally duplicate the generation of some. The duplication wasn't as bad as the ignoring them. But Harold and Larry and the others worked out the details of the other algorithm, and then we were back to the property, the coverage property that we wanted. And kept adding in the chemical knowledge. We did a series of experiments. The critical series of experiments started in around 1966 and ended around didn't end. It was, I reflected on it in the, roughly speaking, the spring of 1968, trying to ask myself, what did we really do? This was because Donald Mickey was having a conference in Edinburgh, machine intelligence workshop, something or other.
One of his series.
One of his series. And he had heard about Dendral from me or somebody. And
Well, he had been to Stanford visiting.
oh, maybe that's why. And he wanted a paper on it. So we hadn't really published in the AI literature up until that time, although we had given a talk to AI people at Carnegie Mellon. Josh Lederberg and I flew back to Carnegie Mellon at Herb Simon's invitation to give a talk, but in '67. But I thought, gee, we better make this a good paper. So what had we really done? So the question was, what is it that we had really done? Well, I put together, essentially laid out the experimental evidence starting sometime around '66 and ending around that time I mentioned, early '68, going from the first of the chemical molecules where we began to add in Jurassi's knowledge, all the way to the most complicated ones that we were doing at the time. I also wanted to make sure that the AI community read the details of this, not just a high-level gloss, but I wanted to give them the actual structures and the actual detailed data. So the 1968 paper in Donald's volume is historically, for me, a very important paper, but I'm not sure how much the AI community was able to get through it because it was just full of what looked like a lot of chemistry. But as you saw, these experiments amounted to titrating in more and more and more and more and more and more and more knowledge. And the more you did that, the smarter the program became. That is, in terms of smart, I mean the more relevant became the answers, the right answer showing up. We didn't often, in fact, probably never gave the chemist only one answer. We gave the chemist a few answers, but the better the answers got over time from titrating in a lot of knowledge. So the message of that paper was, in the knowledge lies the power. And I didn't really, I mean, I knew I was using Bacon's words, but I didn't really mean the same orientation as Bacon. Bacon was talking about political power, but I was just using the phrase as a catchphrase, in the knowledge lies the power, which means we had a pretty much of a vanilla-flavored generate and test process, not that much different from what had come out of the first decade of AI's work, and that didn't bother me at all. I'm a person who believes in building on the scientific results of the past, rather than having to reinvent everything new in your generation. And so I was pretty happy with that, gee, those old ideas really worked. And we just had to tune them a little bit, like with the predictor, to get it to work a little better. But I was very happy with that. And the difference was, we were learning how to represent the knowledge of chemistry, and we were learning how to represent it in a very nice way, very high-level symbolic way, where you could actually see exactly what the knowledge was. It was, if the molecule was in this shape, that implies, meaning the mass spectrometer will do this, and it will break it up into these pieces. Or if the molecule contains O bond O, then throw away those candidates because they're unstable.
So you noticed a kind of a monotonic increase in the quality of the results as the experiments went along and you added more knowledge, more
Yes.
chemical knowledge.
Yes.
Not more search.
No, not more search. We didn't.
So-
That's right. So we didn't have to do the. We didn't have any fancy search things at all except the pruning and steering. Yeah. Steering meaning if I have some left, what do I look at first? What are the priorities for looking at things? And
So this in the knowledge is the power then informed subsequent AI research that you and your group did.
yeah, so that was the big idea, and that was so in my career that is the huge aha. Oh my God, that's what it is. Now that wasn't the way AI was being done previously. If you look at GPS, for example, which was the hot project of, I don't know, the early 60s or something for AI people, it was a brilliant piece of work. But when it got to the knowledge part, Newell and Simon had allocated it to a relatively small operator difference table, which had maybe in it, I don't know, depending on the domain, 24 facts or something like that in the table.
But in the Donald plus Gerald equals Robert problem, the cryptarithmetic problem, they didn't go out and interview experts on solving cryptarithmetic to find out any particular heuristics that they used.
They didn't. But it is true that Herb Simon read enormously in chess while Newell and Shaw were programming up the chess model. So I sometimes think of Herb Simon sitting there at his desk with all of his books as the first knowledge engineer, but he was mining it out of these books, which is fine. Alex Bernstein was not mining it out of his own head for the chess program.
To get a little more information on Dendral, the input would then be typically a mass spectrogram and perhaps the chemical formula.
Yes. No, the input, yes.
And then the output would be some structure, or maybe a group of structures. And usually the structure that an expert chemist would come up with for that mass spectrogram and that formula would be among that small list.
That's correct.
Which could have been a list of millions, but you were able to pare it down with all of this knowledge to a list of half a dozen or whatever.
That's correct.
And now what was
incidentally, I was calling that hypothesis formation. That is single spectrum, which is my data set today, to my answer today. That's my answer forms a hypothesis to explain that data. But the theory was the theory of what gave rise. The theory was the generator of the knowledge, but we didn't have a theory program at the time. We did later in Metadendral.
Now, what were the size in, say, molecular weight of some of the more complex compounds that the Dendral in those days could handle?
Oh boy,
They were big compounds.
Yeah,
They weren't proteins. They were
no.
not that big.
But let's say in my memory sticks the fact that C23 was the largest one that we ever tried to handle. Remember, we were working on 1/nth of a PDP-10 or PDP-20, which is a trivial amount of computing compared with what even our desktop delivers today. So we were hesitant to get into very large combinatorial spaces. So I think C23 was the largest one we tried. But I'm not sure about that. It may have been a good deal smaller than that.
Let's move on to what some of the follow-on to the Dendral years were, especially now armed with this important idea that knowledge is extremely important, and you also coined the phrase knowledge engineering. Can we talk a little bit about what was done under the general banner of knowledge engineering? There was, I guess Metadendral came along. You wanted to learn some of these rules.
So, yeah. Let me separate Metadendral from what I would call mainstream knowledge engineering. Metadendral was the culmination of that dream of the early to mid 60s that had to do with theory formation. The conception was that you had a problem solver, call it Dendral, that took some inputs and produced an output. In doing so, it used a layer, which I didn't give a name to, but Newell later called the knowledge level, of knowledge that it was using to steer the search and prune the search and so on. That knowledge got in there because we interviewed people. How did the people originally get the knowledge? How did Jurassic get that knowledge? By looking at thousands of spectra. So we wanted a program that would look at thousands of mass spectra and infer the knowledge of mass spectrometry that Dendral could use to solve individual hypothesis formation problems. And we did it, but only for a narrow class of compounds. A class of compounds called ketoandrostanes. We were able to infer, so what we used was a generate and test model for that, where since we had several years of experience with representing the knowledge of Dendral, namely the knowledge necessary to solve that problem, we knew what its form was, we could then generate objects of that form exhaustively and irredundantly. And we could prune the space by using now thousands of spectra to prune that search space. So that's what we did. And what fell out of that was a handful of rules for ketoandrostanes. I can't remember exactly how many. But we were able to publish that as new knowledge of mass spectrometry in the Journal of the American Chemical Society, without giving much credit to, and only in a footnote, that a program, Metadendral, actually did this.
Should have been the author.
Now, the triumph there was, at the symbolic level, we were able to do something which had been a dream, to kind of come up with a new piece of science that you could actually publish. And it wasn't special relativity, certainly wasn't general relativity, it was just a little thing that we were able to publish. But still, it was some science. Then the disappointing part of it was, well, the good part was after that, Tom Mitchell cleaned it up. It was kind of it was oriented toward a specific, Metadendral was oriented toward a specific goal that had to do with mass spectrometry. Tom Mitchell, with his version spaces, cleaned it up into a more general thing that other people could use, in concepts other people could use. And I thought that was the beginning of something. Turned out that was the end of something. Nobody followed up on that. The rest of the stuff turned out to be statistical machine learning theory. What does that have to do with?
Well,
anyway, so to me that was a tremendous disappointment.
When you're thinking about Metadendral and the problem, say, that it was involved with, namely trying to come up with scientific ideas, the knowledge that scientists have, well, that itself is a problem. And could you interview scientists to ask them what heuristics, what knowledge, what meta-knowledge they had about coming up with, how did Jurassic decide to, are there any heuristics that would have helped Jurassic learn all of those rules?
There are two answers to that. The first is absolutely yes. Absolutely. And that leads me to say something quite general, which I'll say in a minute. But specifically for Metadendral, we actually did talk to them about how do you, if these were the alternatives, how do you prune that space of possibilities? And we did get some good ideas from them. But the general point that I'd like to make from what you just said was, that I am not at all a believer in this thing called tacit knowledge, which has a history in philosophy, and it comes up, oh, I don't know, 10 times a year you'll see it in various writings of people who think they're writing about AI. I just don't believe it. That it's tacit while you're not interviewing the person. It's tacit while, yeah, sure, the person uses it and doesn't really know, that person doesn't even know they're using that knowledge, but you can interview that person in the context of specific situations and dig it out.
Dig it out.
And there's no reason you can't dig it out, and that's what knowledge engineering is all about.
You can declarativize it in some way or another.
Yeah, and
Now,
what I called knowledge engineering, Donald Mickey at one point called knowledge mining, which has a better feel to it. You're actually chipping away in the
Now, during these days of the Dendral project and up through Metadendral, during some of the early part of that period, you had this other job of being computer center director. Do you want to say anything at all about that, how you happened to get involved in that job, and what effect it might have had on your research?
Yes. That was the summer of 1965 through, roughly speaking, the end of 1968 or maybe early 69, 68 probably. Paul Armour, who had been head of the computer department at Rand, took over my job. I recruited him to take over and make it a professional, not a professorial activity. George Forsyth had been director of the computer center. When he started the computer science department, he noticed that he couldn't do both, especially since the computer center was about to transition into a new generation of machines and expand. So he really didn't have the time to do that. So he asked around about people who were interested in that role, and for reasons that I just don't understand today, I said I was interested in that role. But it may have been, that was 1965, so I was 29 years old, and it may have been that it was time for me to try out managing something, or maybe it was time to try out being a big shot, or who knows why. I'm not sure exactly what it was, but I got into a big management role, managing a budget of $2 to $2.5 million a year and big equipment that had to run all the time, and it would be a financial disaster to Stanford if it didn't, and we had to sell a lot of time. And anyway, it was a very, plus the fact that IBM was in a very unstable state during the early days of the software of the 360. We were promised a time-sharing system. I knew after a year that we weren't going to get that time-sharing system because I had a thesis student named Nils Nilsson who did a thesis simulating, under my direction, in which he was an operations research student, but he simulated the activity of the proposed 360-67 time-sharing system and we could show in simulation that it wasn't going to work. And we tried to convince IBM to change the system. They wouldn't believe a simulation, and they didn't, and it was a disaster, and we had to switch to a 65 with another another kind of software that I think Stanford is still using, Wilbur. Anyway, it was a tough time, and we did not only one, but we did three. We did the 360-91 at SLAC, where Bill Miller was running the SLAC computer operation. He delegated that job of running the big computer to our center, and then we did the medical school one, where we hired Geo Wiederhold to do the time-sharing system. So that was a big one. And did it detract from my research? The answer is absolutely yes. And looking back, I wouldn't do it again. I mean, research time is so precious and the rewards are so huge that it's silly to fritter it away on managing something.
Well, now we sort of, what I would think of as ending some of the early days at Stanford and transitioning into some of your middle days at Stanford, in which you were involved in various projects, HASP and the various expert systems. Do you want to lead off by talking a little bit about some of them?
Well, I want to get back to answering your question about the rest of knowledge engineering. I said, let's put Metadendral aside. And then we started another set of experiments, partly opportunistically, that is partly based on what problem came up and who wanted to do what. We did a rather systematic search for, back up. One swallow doth not a summer make, and one dendral doth not a solid piece of science make. You have to try it out on other things. So we had good connections into the medical school with Lederberg as being a co-PI on all of our work. And we started searching in different areas of biomedicine for relevant problems. For example, the whole question, one came up with the whole question of drug interactions. Well, it turned out that drug interactions were an interesting problem, but it could be solved another way with big table lookups, and there wasn't any advantage of solving it. No virtue and a lot of difficulties.
Not a sandbox for working on induction.
Yeah. But it turned out that the person we contacted, as we did this search for that particular problem, was a professor of pharmacology named Stanley Cohen. And Stanley Cohen eventually became world famous as the co-inventor of the first methods of genetic engineering with Boyer. And in the middle, from the time we knew him in drug interactions to the time he became this world famous guy, he was interested in AI, and he particularly worked with one of our students, Ted Shortliff, MD, PhD student, on AI methods for doing diagnosis and therapy of bacterial infections, where Stan was the provider of the, he was the person whose knowledge was being mined. Plus, not just Stan, it was Stan plus other physicians in that area, in the infectious diseases area of the medical school, and that led to mycin. So it was a combination of Stan's interest and Ted's interest in doing that. Ted knew the language of doctors. He knew as a medical student, and
he was a medical student at the time. Right?
Medical student at the time, and he also knew computer science ideas, and he was interested in AI, so that was an opportunity. Then Larry Roberts was directing the Information Processing Techniques Office at DARPA. It's one of the successors of, well, after Bob Taylor, Larry Roberts took over. And Larry was facing so Larry knew about the Dendral success. And Larry abstracted it in the form of, you have a spectrum, you got an answer.
I got a problem like that, huh?
Forget the details. Yeah, I have a problem like that. I have large numbers of spectra coming from hydrophones buried deep down out on the continental shelf. They're sending signals back to the shore. Those signals are being processed by a fast Fourier transform and mini computers into frequency distributions over time. And I have each one, I have beams of them, and there are lots of beams. And from that, I have to decide what kind of enemy submarine is out there in the ocean, in an ocean that is just roiling with sound, so that when you try to listen to it with your ears, you just don't hear anything. It's just one mess of sound and a Soviet submarine that's trying to be as quiet as it can. And that's like Dendral. I mean, Dendral was a clean data, couldn't be better, nice black and white lines of molecular data, and a nice generating algorithm for generating candidates. And here's Larry saying the same problem, isn't it? So anyway, he wanted me to work on this problem, and we did. We said, okay, let's give it a try. And it was a classified problem, so it was done off campus at Systems Control Incorporated. Incidentally, for those of you who are watching this program 50 years from now, the reason the classified work went off campus was student riots that took place during the Vietnam War, which, believe it or not, for those of you 50 years from now, was a war that took place in the late 1960s, in which millions of young people in the United States were very upset with this war. So they were rioting and destroying campuses. And Stanford, yes, did get destroyed, but also didn't want the rest of it to get destroyed, so they unloaded classified research by A, deciding it shouldn't happen on campus, and B, selling SRI, Stanford Research Institute, to itself to become SRI International and get all the classified work that was on campus into SRI. This work, so our work was done off campus, and it was the problem of tremendous amounts of hydrophone data. There is a single answer, or not a single answer, but a small number of answers. It's a Soviet submarine of type X, Y, and Z, traveling at so many kilometers per hour, passing by Cape Mendocino right now. And here's the reason I believe that, the long explanation that came from the inferential argument. And the knowledge came from people who were experienced in doing that. They knew the big intelligence books that had all the information in there about what these submarines had on them and what noises they made, and they had experience on what neighboring stations told each other along the coast, and they had experience with what the U.S. Navy did along the coast, so that you could subtract out our own noises from the ocean, and what kind of animal noises there were in the ocean, and all the other stuff that you would want to account for.
Plus probably the results from an hour ago or 10 minutes ago, which would have some effect probably on what the results now would be.
Yeah, I guess so, yeah. Right, because sound propagation is what you're talking about.
And tracks, a particular submarine that might have been identified off the Mendocino coast 10 minutes ago is not going to be off San Diego
right.
Now.
And so there was a lot of that kind of knowledge in the program too. Mm-hmm. That is, the submarine is a physical object. Yeah. What can it do and what can't it do? Mm-hmm. And the ocean itself is a physical object. So if you're tracking the submarine and you have a hypothesis as to what you're tracking and where it's going, and somehow the sound shuts off, well, don't worry about it. Don't junk your hypothesis right away, because the submarine may have just gone behind a seamount. Mm-hmm. And, oh, by the way, we know from the past Soviet submarines love to hide behind seamounts. Mm-hmm. So they don't just pass the seamount, mm-hmm. they stop mm-hmm. behind the seamount just to get you confused. And so just wait a while and then decrement the credibility of your hypothesis over time. And after an hour, you can say, well, I don't believe that anymore. I'm going to form a new hypothesis. But otherwise, predict the track just where the submarine was going.
So this certainly was a hypothesis formation problem, an induction problem of the sort you were interested in anyway.
And so, to my great surprise, it was just I couldn't believe how successful it was. Mm-hmm. And I just didn't believe, that was the hardest problem I had ever faced. I couldn't believe that we could do this.
But you used a particularly interesting AI technology.
So the technology, I tried the generate and test strategy. You give a guy a hammer, and he hammers one nail with it, the next nail he's going to hammer, mm-hmm. use the same hammer. Well, the same hammer, generate and test, didn't work. Mm-hmm. Because what are you going to generate? What are the candidate solutions to this thing? Submarines of any kind anywhere?
There's no legal move generator.
Yeah, there's no legal move generator. So we had to have a piecemeal, opportunistic solution, grabbing onto any data or any inference that you could grab onto, and building up an inferential or symbolic complex of how to say this, what you believe in at what layer of abstraction. Like, what do you believe about the fleet? What do you believe about this particular submarine? What do you believe about the machinery in the submarine? What do you believe about the lines that you're seeing in the spectrum? Well, fortunately, right at that time, something just like that had popped up at Carnegie Mellon in the speech understanding project that was being run with DARPA money. It was called Hearsay. It was a product of Lee Ehrman and Raj Reddy and Victor Lesser and Rick Hayes Roth, which designated such layers and a problem-solving method for working between the layers. Now, the layers for them were things like the pragmatics layer and the semantics layer and the lexical layer and the, that is the word layer, and the phonetics layer, and eventually terminating down here in the signal itself, the segments of the speech sound wave. So, and the inference method was top down and bottom up, all happening at, intermixed. So if you knew something about the lexical layer, that is the words, you could then infer something about what phonemes would be in those words. Particularly if you have a dictionary, it gives you pretty much the pronunciation, and you can infer exactly what the phoneme should be from that. And from the phonemes, you could predict lower levels of what the sound should look like, and you could work top down that way. But you could also work bottom up. If you saw some patterns in the signal, you can say, that's this kind of a phoneme, which phoneme wasn't the right word for that level, but it popped up into the phoneme level, and then from there into the lexical level. You could make hypotheses going bottom up. When you mix the two, you get a very powerful mix of expectation-driven reasoning by looking top-down and inductive reasoning looking bottom-up. Makes a very powerful problem-solving method. And you could also organize since you're dealing with a serial computer, you can organize all of this activity into an agenda and saying what's the priority? What should you look at first, what next, and what next?
I mean, you had a parallel computer. Some of these things could be done in parallel.
And we tried that in the 80s with our parallel blackboards in our project. Anyway, we modified the Carnegie Mellon idea. Carnegie Mellon actually didn't use their idea in the speech understanding product that they produced. They used another idea called ARPA, which was another kind of search idea, beam search idea, with using dynamic programming as a selection mechanism. But we weren't constrained by the real-time problem that they had with speech understanding. We had forever to make these calculations because the submarine was moseying along from Russia to the US. I mean, it was thinking it was going fast, but going through the ocean is a pretty slow process. So we had forever to make these calculations. So we could use the whole hearsay type mechanism. And it worked really well. Like you just said that when it came time to, when the DARPA was thinking about parallel computing, we thought of parallelizing blackboards. And we did export the methods. We abstracted some methods from the classified work that we did, packaged them up into a piece of software called AGE, A-G-E, and that was the Blackboard framework of choice for several years until basically it was, what took over was a couple modifications of it done by Barbara Hayes Roth called BB1 and BBK in our laboratory. AGE was done by Penny Nee, who was the chief engineer of the sonar signal processing project over at Systems Control.
So in Blackboard, not only was it successful with the sonar processing, but it was used in many other applications, right?
So again, like I said before, one swallow doesn't make a summer, and you got to test this thing out in various ways, and we wanted the toughest possible test outside of the sonar context. And so we found a problem that I had known some people in X-ray crystallography at UC San Diego by virtue of my having served on an NIH committee with a person, an X-ray crystallographer. And I knew about his inferential task. I knew what it was, what he was trying to do in inferring the three-dimensional, notice geometry, not topology, the three-dimensional structure of proteins in crystals from the X-ray crystallographic data, the electron density that was that you got from doing X-ray crystallography on the protein crystals. Many of you know about this because you've read Watson's book, The Double Helix, I think it was by Watson, not Watson and
Yeah.
Crick, Watson's book on the double helix, in which one of the British scientists has done that kind of crystallography on what eventually turned out to be the DNA, and Watson basically stole the pictures from Rosalind Franklin, who should have gotten the Nobel Prize along with Watson and Crick, but she died early. But she had done the X-ray crystallography in her lab of the DNA that gave Watson and Crick the idea of how this geometry worked. We were trying to do that with our program, Chrysalis. The people who we were working with had, I believe they were the first people to have done the structure of hemoglobin. There weren't too many of these structures that had been inferred at the time, because it was really a tremendous amount of work to do this, and a lot of work crystallizing the protein. Anyway, we used the Blackboard model to do in two ways. One was to analyze the electron density itself, so that was very close to the data, and the other was to infer. So you got partial results by analyzing the physical data, and part of the results by working up and down the chemistry. So we had intersecting blackboards, in which one blackboard had the levels of chemical abstraction, the other blackboard had levels of crystallographic abstraction, and at some points they would intersect. So where the crystallography was making some inferences, the chemistry was also making the same inferences. We could believe in those notes, because both were telling the same story. So that was intersecting blackboards. That was the first and only time that's been used. And then Blackboard became a little industry. There was one of the UMass Amherst students working with Vic Lesser started a Blackboard company, selling Blackboard software during the era of expert system construction.
It's used quite a bit throughout computer science.
Yeah.
Matter of fact, as you and I both know, it has resurfaced a little. Some of the ideas of top-down and bottom-up simultaneous working has resurfaced a bit in some of the recent work on brain modeling.
This was Hawkins published a book. Jeff Hawkins published a book on. Basically, the book starts out by saying AI hasn't done much, and all of the next chapters are bringing in AI results and showing how they apply to the brain. So I'd appreciate it if Hawkins would actually reference the AI stuff a little more.
So we had several of these things going on at the same, during this period. Ed, there was the metadendral work, the work on sonar, the work on bacterial infections with Ed Shortleaf. Also, you were beginning to think a little bit about molecular genetics, and that led to some interesting programs also, right?
So the project that led to was called MolGen. For years, I had been asking my colleague Josh Lederberg, how come you have been recommending to us that we work in the chemistry or medical areas when in fact you are a geneticist, in fact a Nobel Prize winning geneticist. How come we're not working in your area where you yourself can be the expert? And I humorously codified a law called Lederberg's Law, which is everything is automatable up to but not including what I do. But eventually Josh said, yes, let's do it. And that had to do with the invention of the genetic engineering method of Boyer and Cohen. And Josh's view was that starts a new era. And if it starts a new era, we can get in on the bottom. That is, if we have to do knowledge accumulation, knowledge engineering, don't start where you have a huge pile of knowledge like in genetics. Start where you have almost no knowledge, which is genetic engineering. That got us into MolGen. There were two theses done in MolGen. first of all, MALGEN was the first computer science project in what now, anywhere, in what is now called computational molecular biology. There were some other computer efforts in genetic departments at places like the University of Wisconsin, where geneticists were doing also what we did, which is initially searching of genetic sequences for interesting information about the occurrence of bases in loops and isomorphisms and things like that, homomorphisms. That was a set of tools that led to, that was extremely valuable, and on our network time-sharing system soon had hundreds of users in the biological community. Those tools were called SEQ, for sequence analysis. And it led to the formation of a company called IntelliGenetics, which offered those services for sale to the biological community. In addition, there were two significant PhD theses involved in the planning of experiments in genetic engineering. One of those theses was what you might call plan by recipe, very much similar to what Roger Schenck was telling us ought to be the way that we looked at AI problem solving and planning. And the other was a much more basic view of building up a plan from the bottom up in very similar ways to the way SRI had been doing it and other people in planning. The theses of Mark Stefik, which was the one closer to the traditional methods, and the one by Peter Friedland, which was more skeletal planning, planning by recipe or story.
Okay.